So for the introduction, in fact, that morning, Christophe Béard and Mr. Noreux explained a lot of things. Okay, I will try to go more quickly on the first part of my talk. I will introduce first the rationale for the future nuclear fuel cycle in view of sustainability, what we are calling to generation 4. And after I will make a focus on ASWID program on which CEA with several partners, EDF, Areva, but more other, I will get back on that. We are focusing our efforts in order to prepare generation 4 commercial reactor. On that slide, first, today we are considering a fleet with generation 2 and 3 reactors in which we are mainly performing mono-recycling of plutonium in light water reactor by using MOX fuel. It is the first step towards uranium resource saving, and we are preparing an efficient waste conditioning. The generation 4 reactors, as explained that morning, is the first step in order to have a large flexibility that will allow plutonium multi-recycling and depleting uranium large use. We are considering a multi-fuel cycle in fast reactor, as it has been explained that morning. And by such fast reactor, we can have a major improvement for the resource saving, not only plutonium, but also depleted uranium. I will go back on that. It is a step for energetic independence and economic stability for the electricity production. Another step could be the minor actinide burning in some fast reactor. Donc, for some countries, mainly plutonium multi-recycling is considered, and in other countries, we are considering the combination of the two options, plutonium multi-recycling and minor actinide burning. By this second step, we have the ability to decrease stock of nuclear waste and to have an optimization of nuclear waste disposal. It is important relative to the public acceptance. If we are considering the cycle with light water reactor, it is on that part, we have every year, it is the data on that slide are the current data relative to the current French fleet. Now, we have a need of large quantity of natural uranium, about 8,000 tons per year. And we have several steps, uranium conversion, uranium enrichment, fuel fabrication, and only a small part today of plutonium is reused in the cycle under the MOX format. In the case of a fleet with only fast reactor, we can simplify strongly the cycle. And in fact, we can have a recycling of plutonium and uranium, and at each turn, we need only a few tons of depleted uranium. So for such fleet, in France, for instance, we have a very large amount of depleted uranium. Or it is it is not the case for every country in the world, but in France, we can simplify strongly the fast reactor cycle. Obviously, we will not switch only in short term from one cycle to another cycle. So we are working on several scenarios that can lead to the light water cycle, current cycle, to an optimized cycle with fast reactor. Some figure has been shown that morning by Christophe Béard and Philippe Noreux. We have several scenarios under discussion with EDF, Areva, and the French government. Based on the current plutonium stockpile, we can start the deployment of sodium-cooled fast reactor. The deployment will depend, in fact, on several economical conditions, obviously. That slide just point out another interest relative to the fast reactor. It is the potential influence on the repository footprint. It has been presented that morning by some speakers, and it is another figure that we can have a very strong influence, impact on the repository footprint. It is important because we can consider, due to some public acceptance difficulties, that the surfaces will be should be optimized in practice. Only fast neutron reactors are able to manage and to optimize, in fact, the use of plutonium under the different isotopes and depleted uranium. It is very important to keep in mind that. I just go quickly because it has been explained that morning. Just if you want more detail, on the CEA website, you can find a public document. First is the so-called Dossier 2012. It is a summary of the work performed by CEA, EDF, Areva, and ANDRA under the French Act of 2006 on the waste management. And an updated has been provided to the French government in June 2015, and it is too available on the CEA website. Now, in France, we are, in order to prepare the Generation 4 reactors, we decided with EDF and Areva and with the French government to focus our efforts on sodium-cooled fast reactors. We have other activities related to gas-cooled fast reactor, for instance, mainly in partnership with V4G4 consortium in Eastern Europa in order to prepare Allegro demonstration reactor, for instance. And obviously, we have some survey of other potential fast reactors, mainly under the frame of some European projects. In agreement with the French government and EDF and CEA, it has been decided to focus on sodium-cooled fast reactor because we have a large feedback experience with Phoenix and Super Phoenix realization and some other projects. And the other important point, when the program has been launched in 2009, the willingness of the French government was to have a commercial reactor available about 2050, 2060, about the middle of the century. And only sodium-cooled fast reactor based on the existing operational feedback allow to have a commercial reactor available at the middle of the century. What are the objectives of ASWID? ASWID means Advanced Sodium Technological Reactor for Industrial Demonstration. Donc it is a technological demonstration reactor. It is not a first of a kind. Donc, based on the design option for ASWID, and due to the fact we will have several years before launching a commercial reactor design and building, we have time, in fact, to improve some design option based on the progress of the R&D. So we can have some differences between ASWID and the first of a kind of commercial reactor. We would like to integrate French and international feedback. I will provide to you some example. It is a Generation 4 system. First, we have obviously to make some progresses on safety. In France, we have a continuous increase on the safety. We are expecting to start the building phase of ASWID about 2023, 2025. It will be the same period for the deployment of some EPR reactor in France. So we are considering an equivalent safety level. We have to take into account some progresses of sodium reactor specificities. We have to integrate Fukushima accident feedback and to improve the robustness of the safety demonstration, specifically for the practically eliminated situation, for instance. Durability. ASWID is developed in order to promote closed fuel cycle, and we have to demonstrate industrially the plutonium material recycling. Obviously, we would like to obtain a load factor of about 80% after the first years of learning years. 80% will include influence of experimental program. Because in that ASWID program, we plan to use ASWID as it will be the alone fast reactor available in France, but to make some irradiation program in order to prepare the commercial reactor. These irradiation services and experimental options could have an influence of 10% on availability rate, for instance. I will get it back specifically. I will make a focus on IZIR. If the French government decided to continue on the transmutation of nuclear waste, we will perform qualification and demonstration on minor actinide transmutation in ASWID. Just some focus on some innovation compared to Phoenix and Super Phoenix or international feedback. In the fast core, in fact, the neutronics, from the neutronical point of view, we have usually large positive sodium word wars or word wars. In Phoenix and Super Phoenix, we have about $5 of sodium word wars. We define, and with our partners, EDF and Areva, a low sodium word wars. It is in best estimate about $0. And in case of unprotected loss of flow or other situation without protection, we can avoid some power increase during the first period. In some situation, we will have, in hypothetical situation of severe accident, we will have a thermal degradation, and we can avoid neutronics excursion, power excursion. It is based on some heterogeneous design and several design options. Today, we are performing qualification program. First, we are refurbishing Mazurka, a mock-up at Cadarache, in order to qualify neutronic calculation routes, in order to confirm that this heterogeneity combination could allow to have to reach a $0 core. And we are performing post-irradiation examination on hot lab at CEA, LECA, and LECI of heterogeneous spins with high content of plutonium irradiated in the past in Phoenix. And we are preparing some specific irradiation in existing fast reactor currently in the world, mainly in Russia, but we have some discussion with our partners, Japanese partners. Concerning inspection, sodium is opaque. So we have some difficulties in order to survey what happens inside the main vessel. Now we work on that concern at the first stages of the design by some design optimization with some dedicated paths in order to allow some sensor, to allow to bring some sensor inside sodium close to some wells that we would like to inspect, and we are working on the development of some carriers, dedicated carriers. Concerning severe accidents, we have obviously the objective to avoid any early and significant releases in case of severe accident. For that, we are considering an internal core catcher with a full capability to welcome all the corium. Donc it is an improvement of superphénix core catcher. And in order to ensure the movement of the corium from the core area to the core catcher, we are designing some corium transfer devices with our partners, Areva. Due to some specificities in the CFV core, the low sodium Woodworth core, and its specific path, we have to develop new software and to perform new experiments in order to complete our qualification database. Donc we have a joint development with Japan for a new severe accident reference code called CIMER5 inside the Season platform, and we plan to build a new facility called Plinius 2 in Cadarache, able to manage 500 kilograms of corium. Concerning the power conversion system, I think you have in mind the reactivity between sodium and water. Donc in case of steam generator, we have a very thin wall between water and sodium. In Phoenix, for instance, we had in the past 5 sodium-water reactions without safety consequences, but it is a public concern. Donc, in order, it is not really a safety concern. In the past, any sodium-water reaction occur in a fast reactor in the world doesn't provide a risk on the safety. There is only an availability concern. But it is a public concern, and due to the question relative to the public acceptance for new sodium fast reactor, in parallel to the development of steam-water power conversion system, we are developing a gas power conversion system. And for that, we are considering a compact sodium gas heat exchanger. Gas is nitrogen in our case. And after, we have a gas turbine. We have a relatively compact system. As we have no close location between sodium and water, we have a physical elimination of the risk of sodium-water reaction. And nitrogen and sodium are chemical inert. So we manufacture recently 3 mock-up of the most complex component. It is a plate exchanger, and it is a 3 mock-up of this part here is under qualification under a Diademo facility at Cadarache. Okay, it is a small mock-up, less than 100 kilowatts, and we are working on the manufacturing of a mock-up of that exchanger with a power of 12 megawatt, thermal megawatt, and it will be qualified in KEOPS facilities. KEOPS is under building at Cadarache with with a large quantity of sodium for large-scale experiments. At the end of 2015, it was the end of the conceptual design phase. We provided to the French government, because most part of our funds is coming from the French government, 70%, about 70%. And we provide to the French government a synthesis file, 2 synthesis files. One is a strategical synthesis file. It is a public document now, available on the website, and technical synthesis file, not public document, that provide the summary of the conceptual design phase and the description of the next phases. We obtained the authorization of the French government to proceed until the end of 2019 of the basic design phase. Just some figure of what is the look of Astrid at the end of the conceptual design phase. We have a pool type sodium cooled fast reactor. All the active sodium, all the sodium of the primary circuit is inside the main vessel. we have here some intermediate heat exchanger in which we have the exchange between the primary circuit and the secondary circuit. The secondary circuit is in sodium, and after there is a transfer to steam water by a steam generator in case of steam water power conversion system, or a transfer to nitrogen in case of gas power conversion system. Today we are working on the two with the two we have two designs, two possible designs. The cold plenum here is in the lower part. We have a separation between the hot plenum and the cold plenum. We have a primary pump. The primary pump will insert the cold sodium in the diagrid, and after the sodium go through the core. We have an increase of the temperature of about 150 degrees Celsius. And here we have the hot plenum, and after an exchange with. Okay, we are considering a concept with 1,500 thermal megawatt. It is about 600 electrical megawatt. It depends on the power conversion system. Donc we have an intermediate sodium circuit, the low sodium Woodworth, MOX fuel, in-vessel core catcher, you can see here. We have a diversification of the decay removal system with two systems inside the main vessel and one system through the main vessel. Our objective is to have a practical elimination of the loss for a long period of the decay removal function. Internal storage and fuel handling in gas. And today, some optimization are ongoing. We have 3 primary pumps, 4 intermediate heat exchanger, 4 secondary circuits, and 5 decay removal circuits. Obviously, we have some experimental capabilities in order to qualify some transmutation fuel, fertile fuel, or burner subassembly. It is a view of the reactor building with main vessel. We have anti-seismic raft, and we are considering a polar table. The polar table, below the polar table, we have control of the atmosphere. We have very low quantity of oxygen, and in case of sodium leakage on the roof, in that case, we will avoid a very large sodium fire from safety point of view. It is an example of the balance of plant with a turbomachinery building in case of steam water power conversion system. We have the fuel building and just close the handling, special handling building and so on. Okay, it is an example of balance of plant. CEA is in charge of ASWID program under the frame of a specific agreement between the French government and CEA signed in 2010 between the French Prime Minister and the CEA. We obtained a dedicated fund for that, but we are not working alone. CEA is not relevant for nuclear island design, for civil engineering works, and so on. So we develop a set of partnerships. First, we have a lot of, on the right side, a lot of industrial partnership. I will get back on that. We develop a second set of partnership dedicated on the R&D in support to the qualification of some ASWID innovations. Donc, it is called ARDECO, ASWID R&D European Cooperation, because it is mainly European, but in fact, no, it is not only European. We are working with Japan strongly. ARDECO and industrial partners are working with CEA under specific agreements that cover IP, confidentiality, and so on. And for the generic R&D, we have a lot of international cooperation, including cooperation inside Generation 4 International Forum, European Framework, or other bilateral partners. For instance, with Russia, we are using some irradiation tools, irradiation reactor in Russia, because in France today and Europe today we have no more fast reactor capabilities. It is a current organization. CEA is responsible of ASWID project. Donc we have a strategic management. Donc I am in charge of the strategic management from the operational point of view. And we have a dedicated team at Cadarache, ASWID project team, in charge of operational management of each partners and industrial and they have the function of industrial architect. We have the assistance of EDF specifically on that. After, we have several batches. CEA kept the responsibility of the core design, and we have a support of Areva NP. Areva NP is in charge of the nuclear island design with two main partners, Japan with GAA, MHI, and MFBR, and Alsan SEIV for the hot cell. Alstom, now included inside the GE, is in charge of the power conversion system. Bouygues is in charge of the civil engineering, and Jacobs is in charge of balance of plant. These partners are funding partly their contribution. It is not subcontractors. Concerning some innovative components, we need to ensure the capability to manufacture in the future some innovations. Donc we develop a set of specific partners that are focused their effort on some components. Toshiba, for instance, on large electromagnetical pump for the secondary circuit. CNIM on the capability to manufacture, for instance, the primary fuel handling system, for instance. Dynetics, some innovative leakness seal. Velan, large sodium valve for isolation of the secondary circuit. And ONET on robotics for inspection, for instance. And the last specific partner is Airbus. Airbus is not involved in the nuclear today, but ASWID, as I said in the previous slide, for ASWID we have a very large, ambitious objective for availability rate. ASWID is a demonstration reactor. It is a kind of prototype. Airbus, Defense and Space, has some skills to develop unique satellites with very high expectation for availability rate. So we are using the availability methodologies used in the spatial and military domain, and we are applying it to ASWID in order to try to reach our objective of 80% of availability rate. All these partners are providing a list of R&D needs in order to support the qualification. For that, the R&D list is assessed by CEA in charge of the program, and we have a specific team in charge to coordinate all the R&D in support to the qualification with the support of Ardeco, EDF, and Japan, for instance. We have today 14 industrial partners and 6 R&D bilateral partners. In parallel of ASWID, we are developing the fuel cycle. So we are considering for the first 20 years of operation of ASWID the use of current fuel facility in France. For instance, we are working, if it is possible, to adapt Melox in Marcoule for specific fuel for ASWID. It is not an easy question because we have not the same plutonium content. That morning, Philippe Noreux spoke about a TCP workshop at La Hague, and we have a strong relationship with a TCP designer for welcoming as in order to include in the specification the processing of ASWID spent fuel. And we have a second step of studies in order to prepare a future dedicated facility for the different types of MOX fuel for light water reactor and fast reactors, coming from light water and fast reactors. and in order to simplify the process on the second step. To conclude, so nuclear energy is today a well-proven source of large baseload electricity with no emission of carbon. And it is one of the pillars of the current now French low carbon energy mix. It remains. The closed-loop cycle associated with fast neutron reactor will lead to drastic improvement in uranium and plutonium resource management. It could lead, depending on some decision on nuclear policy, it could lead to important reduction in footprint and radiotoxicity of final waste. The French program on Generation 4 is based on Astrid program. The basic design phase is ongoing until end of 2019. It is the end of the current agreement between the French government and CEA. So we are working today with French government and with EDF, Areva, Japan, specifically, to the preparation of the next phases and the schedule and the funding scheme. And we expect to be able to start about 2023 the building phase. Thank you very much for your attention.